Hello and welcome to this presentation on Carl Waldspurger's and William Weil's paper on stride scheduling, deterministic proportional shared resource management. This presentation explains stride scheduling, which is a deterministic scheduling technique that provides the same flexible resource management strategies employed by lottery scheduling. I'll touch briefly on lottery scheduling, but that isn't the scope of this presentation. Proportional share scheduling attempts to make the resource consumption rates of active clients proportional to the relative shares that they're allocated. Ideally, if an active client, let's say a process, is twice as important than another, it should receive twice a share of the CPU. Rather than using standard periods of time, for example, seconds, resources are allocated and received in discrete time slices. Waldspurger refers to the duration of a time slice as a quantum. There are two types Waldspurger proposed in 1995. The first is lottery scheduling. Processes are random or ran by a random choice with probabilities of selection proportionally favoring those jobs, giving higher priority. For example, if there's three clients, client A has three times the priority as client C, and client B has twice the priority of client C. You could, for example, use a six-sided die, give client A numbers 1, 2, and 3, B 4 and 5, and C 6, and then roll the die. After you roll it enough times, eventually, client A will always get three times the amount that client C does, and B twice the amount that C does. Instead of dice, Waldspurger presents resource rates by tickets. Tickets are abstract objects issued in different amounts assigned proportional to relative priority between clients. Again, 3 to 2 to 1 ticket allocations. You can think of tickets as being placed in a bucket, and a ticket is drawn to determine who goes next. It is important to remember, though, that drawn tickets get replaced into the bucket to ensure that proportions and probabilities are maintained. Stride scheduling attempts to eliminate random allocation of resources by using a deterministic approach to allocate resources rather than a probabilistic approach that lottery uses. Because of randomness, lottery scheduling has significant variability of allocations from ideal. For example, in the chart, we see the 3 to 2 to 1 allocation. Again, client A gets sides 1, 2, and 3 of a die, B 4 and 5, and C gets 6. If we roll that die 100 times, ideally, client A should get exactly 50% of the time, client B 33 and a third, and client C 16 and 2/3%. In the charted simulation using a random number generator, we can see the variability represented by a colored line for each client, from the ideal represented by the dashed line for each client. Throughput accuracy, absolute error, causing the allocations from ideal, and the response time variability, absolute error, are discussed in the next slide. For throughput accuracy, under randomized lottery scheduling, the expected value for the absolute error between specified and actual number of allocations for any sets of clients is O of the square root of the number of allocations. This is because the number of lotteries won by a client has a binomial distribution. The probability P that a client holding T tickets will win a given lottery with a total of capital T tickets is simply P equals small t over capital T. After n sub a identical lotteries, the expected number of wins is E of W is equal to number of allocations times the probability, with the variance sigma squared equal to the number of allocations times the probability times 1 minus that probability. Mean error slows down but still grows over time. Response time variability is another important performance metric, which we measure as the elapsed time from a client's completion of one quantum up to and including its completion of another. The expected number of lotteries that a client must wait before its first win is given by the top equation on that chart. It's equal to 1 over the probability, and you can see the variation there and the equation. As you can see, response time is widely distributed because of high variability. So what stride scheduling does is it answers the important need for a deterministic version of lottery scheduling to provide more accurate control over relative throughput rates with lower variability in throughput accuracy and response times. Stride scheduling does this by implementing proportional share control over processor time and other time shared resources that are allocated in discrete time slices called quanta. Waldspurger said he applied elements of rate-based flow control for networks in developing stride scheduling. Waldspurger's paper doesn't provide any explanation of rate-based flow control, so I have provided a link if you want to investigate further. The core idea of stride scheduling is to determine a time interval called a stride that a client must wait between successive allocations. The client with the smallest stride will be scheduled most frequently. A client with half the stride of another will execute twice as quickly. A client with double the stride of another will execute twice as slowly. Strides are represented in virtual time units called passes, measured in quanta, instead of real-time units such as seconds. So let's begin by going over stride scheduling's basic algorithm. Each client has 3 state variables: tickets, stride, and pass. The client's tickets specifies the client's resource allocation relative to other clients. For example, again, the 3 to 2 to 1 allocations of tickets we discussed earlier in lottery scheduling. Client A has 3 times the priority of client C, client B twice that of client C. The client stride is inversely proportional to its number of tickets and represents the interval between selections, and this is measured in passes. We could accurately represent stride as just a reciprocal of tickets. However, Waldspurger believes the use of a high-precision integer for strides is more efficient. Because of relativity and the use of discrete quanta for time slices, he uses a large constant, stride sub 1, to represent stride as an integer corresponding to a minimum ticket allocation of 1. I wouldn't call it more efficient as Waldspurger does, perhaps more effective, since it's easier to visualize a stride as a whole number rather than a fraction, and it's simpler to deal with an integer stride than a floating number programmatically. Therefore, to ensure a high precision integer, the client stride is the inverted ticket value multiplied by this constant stride sub 1. And you can see that equation. Stride sub C is equal to stride sub 1 over ticket sub C. And then finally, client's pass represents the virtual time index for the client's next selection after it uses a process or resource. The client's next pass becomes its current pass plus its stride. Performing the allocation then is simple. The client with the minimum pass is selected. Then he uses the resource for 1 quantum, and then its pass is advanced by its stride. If more than 1 client has the same minimum pass value, then any of them may be selected. Typically, and for the next example I use, if there's a tie, then the client with the highest priority or the most tickets will get selected. This is Waldspurger's stride scheduling example from his paper. Client A is represented by a triangle, B a circle, and C a square. They have a 3 to 2 to 1 ticket ratio. In this example, stride sub 1 will equal 6. Although that's not a large integer, it is a greatest common factor of 3, 2, and 1, and therefore it'll result in integer strides of 2, 3, and 6. For each quantum, the client with the minimum pass value is selected and its pass is advanced by its stride. At the first or initial quantum, each client's pass is set to its stride. Client A is set to 2, B is set to 3, and C is set to 6. We select the client with the lowest pass, which is client A. Client A has a CPU for a quantum, and its pass of 2 is advanced by its stride of 2 to 4. Lowest pass is now held by client B. Client B has a CPU for a quantum, and its pass of 3 is advanced by its stride of 3 to 6. Lowest pass is again held by client A. Client A has a CPU for a quantum, and its pass of 4 is advanced by its stride of 2 to 6. Skipping a couple, at the 6th quanta, the minimum pass is finally held by client C. It uses a CPU for a quantum, and its pass of 6 is advanced by its stride of 6 to 12. At this time, you'll notice that client A was allocated the processor for 3 quanta, client B for 2 quanta, and client C for 1 quanta, directly proportional to the tickets allocated to each resource. In this scenario, this will occur every 6 quanta from the initial quantum, which indicates an allocation error at the total number of tickets or multiple of from the initial quantum will be erased. This is definitely a benefit over lottery scheduling. The basic algorithm does not support dynamic changes in the number of clients competing for the CPU. When clients join and leave at any time, their state must be appropriately modified. Stride scheduling must effectively handle these dynamic changes. Added to the basic algorithm are extensions to add this ability. One extension is the addition of global variables that aggregate the data set of the active clients. The global tickets variable contains a total ticket sum of active clients. The global pass variable maintains the scheduler's current pass. And the global pass advances at the rate of global stride per quantum, where global stride is equal to stride sub 1 over global tickets. In our example, a stride sub 1 of 6 over 3 plus 2 plus 1 tickets gives us a global stride of 1. The global pass advances at this rate. A client state variable called remain is used to store the remaining portion of its stride when a dynamic change occurs. The remain field is the number of passes left before the client's next selection. So when a client leaves the system, remain is the difference between the client's pass and the global pass. When the client rejoins, its new pass value is its remain added to the global pass. So note is that the client's remain is more than its stride, the client gets penalized when it rejoins. And the opposite is true. If the client's remain is less than its stride, the client gets credited when it rejoins. Stride scheduling must also allow for dynamically modifying ticket allocations. When a client's ticket allocation is dynamically changed to a new ticket allocation, its stride and pass values must be recomputed. So as shown in that diagram, the new stride is computed as in the basic algorithm, inversely proportional to new tickets. To determine the new pass, the new remain, which is the remaining portion of the client's current stride, is scaled to reflect the new stride, or remain times new stride divided by old stride. If its ticket allocation would have decreased, then pass would increase, expanding the remain until the client is next selected. So in the basic algorithm, a client might not use its entire allocated quantum and would therefore receive less than its entitled share of the CPU. In this case, stride scheduling accommodates this by using fractional quanta. When a client uses a fraction f of its allocated time quantum, its pass will be advanced by f times stride instead of its whole stride. The client's pass will be increased less, and it will therefore be scheduled sooner. There will be instances where a client could consume more than its allocated quantum. In that case, f is greater than 1. The client's stride will be increased, and it will be scheduled later. Stride scheduling guarantees that the relative throughput error for any pair of clients never exceeds a single quantum. That's a significant improvement over lottery scheduling. However, depending on the distribution of tickets to clients, a large absolute throughput error is still possible. For example, let's consider 101 clients with one very high priority client with an allocation of 100 tickets and 100 low priority clients with a ticket each. This is a ratio of 100 to 1 to 1 to 1 and so on for the rest of the client's ticket allocation. An ideal schedule would minimize absolute error and response time variability by alternating each of the 100 tickets of the high priority clients with each single ticket client. However, as we saw in the standard stride algorithm, the clients are scheduled in order with the lowest pass going first. Assuming stride 1, for this example, the high priority client receives stride equals 1 and consumes the first 100 quanta before any of the other clients receive a single quantum, since their strides all equal 100. So after 100 allocations, the ideal allocation for the 100 ticket client is 50 quanta, while its actual is 100 quanta consumed, which yields a large absolute error of 50 quanta. So a solution Waldspurger describes as hierarchical stride scheduling, which is essentially a recursive application of the basic stride scheduling algorithm. Individual clients are combined up into groups with larger aggregate ticket allocations and correspondingly smaller strides. An allocation is performed by invoking the normal stride scheduling algorithm first among groups and then among the individual clients within groups. In my next slide, we'll consider a balanced binary tree of groups. Each leaf node represents an individual client, and the internal node represents a group of clients, or the leaf nodes that it covers, and contains their aggregate tickets, stride, and pass values. For internal nodes, tickets is a total ticket sum for all of the clients it covers. And stride is equal to strides of 1 over tickets. The pass values for internal nodes are updated whenever the pass value for any of the clients that they cover is modified after consuming the resource. This is an example of hierarchical stride scheduling using a simple binary tree. Strides of 1 constant is set to 480 to ensure integer stride values. 4 clients are allocated tickets of 6, 6, 15, and 5. Each client stride is calculated as strides of 1 over tickets. Initially, each internal node and client pass would be set to its stride. To begin this example, I have already simulated 7 iterations. Notice that each client has been allocated appropriate timed quanta according to their priority, with the highest priority client C getting the most in rough proportion to the lesser priority client's tickets. In this example, we'll run the next pass and consume quanta 8. We start at the root and move down to the next internal node with the minimum pass value. This is the one on the right with the pass value of 120, which is less than 160. Next, we move down to the client with the lowest pass value, which is client C, with a pass value of 128. Client C is now allocated quanta 8, which it consumes. And finally, all pass values are updated up to the root. and the next iteration can begin. This is a comparison of lottery versus stride scheduling cumulative quanta over time. These charts show simulation results for 100 allocations involving 3 clients, A, B, and C, with a 3 to 2 to 1 allocation. Again, the dashed lines represent ideal proportional share behavior. And you can see that the randomized lottery scheduler shows significant allocation variability, while the deterministic stride scheduler exhibits precise behavior. This is a comparison of lottery versus stride scheduling throughput accuracy. The top charts display 2 clients with 7 to 3 ticket ratio, and the bottom chart shows a 19 to 1 ticket ratios over 1,000 allocations. Only the first 100 quanta are shown for the stride scheduler, since its quantization error is deterministic and periodic. Mean lottery error averaged over 1,000 separate runs is chart A. Chart B is stride scheduler error for a single 7 to 3 to run 1, and that's a huge improvement. Mean lottery schedule error average over 1,000 separate 19 to 1 runs in chart C, and chart D shows stride scheduler error for a single 19 to 1 run. Again, much improved. The randomized lottery scheduler shows significant throughput error, accuracy error, whereas the deterministic stride scheduler, again, exhibits precise behavior. This is a comparison of lottery versus stride scheduling response time distribution. These simulation results for 2 clients with a 7 to 3 ticket ratio over 1 million allocations. In chart A, see client with 7 tickets under lottery scheduling with a mean of 1.43 and a standard deviation of 0.78. In chart B, the client with 7 tickets under stride scheduling also has a mean of 1.43, but improved standard deviation of 0.49. In chart C, the client with 3 tickets under lottery scheduling has a mean of 3.33 and a standard deviation of 2.79. And finally, the client with 3 tickets under stride scheduling in chart D has a mean of 3.33 and a standard deviation of 0.47. There is little to no variability from stride scheduling. So compared to lottery scheduling, stride scheduling achieves much better accuracy over relative throughput rates with much lower response time variability. Stride scheduling implements proportional share control over processor time and other resources by cross-applying elements of rate-based flow control algorithms designed for networks. Stride scheduling supports dynamic changes of clients and tickets. A hierarchical stride scheduling scheme can be used to achieve better throughput accuracy and lower response time variability than prior techniques. So compared to lottery scheduling, stride scheduling is much more complex. Lottery scheduling is stateless, whereas stride scheduling requires state maintenance and careful state updates for dynamic changes. Stride scheduling does provide precise control. One wonders, though, is this needed in scheduling CPU time? How do you determine total tickets and ticket allocations? One area I think it might work great in is data centers. Customers pay for higher speeds and efficiencies, and tickets could be allocated by what service the customer purchased. And thank you for viewing this presentation, and I hope you gained an understanding of stride scheduling.